Hello and welcome to the Maths Primer for Machine Learning Mastery. In this video, we're going to be covering the fundamentals of linear algebra, statistics and probability, calculus, and a little bit of multivariable calculus. So what do you need to know before watching this video? If you have a basic level of high school math, you should be fine. Meaning, if you know algebra and a little bit of geometry, you should definitely be able to follow along with this video. So today we're going to be starting with linear algebra. It's a bit unconventional since linear algebra usually comes after calculus in most curriculums, but I think starting with linear algebra is fundamental to understanding the underlying data structures behind machine learning. So we're going to start off with scalars and vectors. Many of the algebraic and arithmetic operations that you may be used to performing on numbers can be generalized to vectors. So let's start off by defining what are scalars. Scalars are just numbers. They're quantities that have magnitude but no direction. Other than positive or negative. So some examples of scalars can be temperature, distance, speed, or mass. Now, what are vectors? Vectors are just a list of numbers, or a list of scalars. They can be interpreted in a couple ways. A point in space, where the list of numbers identifies the position or coordinates of that point, and an arrow from the origin to that point, or as something with magnitude and direction. For example, velocity, 250 miles per hour northwest. The magnitude would be 250 miles per hour, and the direction would be northwest. So, you can visualize vectors as a directed arrow from the origin to the endpoint represented by the list of numbers. Now, what is the origin? It's just the point 0, 0 on a graph. Vectors can be denoted by a small arrow over a symbol. So the vector A would be written like this. And we're defining it as a list of numbers 4, 3. What does this look like graphically? As I said, vectors can be represented as a directed arrow from the origin to the endpoint represented by the list of numbers. So in this case, vector A is 4, 3. And it would look like an arrow with an x component of 4 and a y component of 3. This is vector A. In this example, the vector, or the list of numbers, was only 2 elements long, 4 and 3. In principle, it could be any length. Now, what is the dimensionality of a vector? Dimensionality. It's just the length of the list. The length of the list of numbers that represent the vector. A is two-dimensional because it is a list of 2 numbers and it lives in a plane. A 3-dimensional vector would be a list of 3 numbers and would reside in a 3D volume. A 27-dimensional vector would be a list of 27 numbers and cannot be visualized since space can only be represented by a 3D space. Now, let's talk about magnitude and direction, the 2 components of a vector. The magnitude of a vector is the distance from the origin to the endpoint of the vector, or just the length. To calculate magnitude, we use the Pythagorean theorem from geometry. It's just x squared plus y squared equals z squared. That is the Pythagorean theorem, where x would be one side of the triangle, y would be another side of the triangle, and z would be the hypotenuse. So to find the length of z, or to find the length of any of the sides, you would just use this formula. So to calculate magnitude, which is represented by these 2 lines on the side of the vector, on each side of the vector, we take the square roots of x squared plus y squared, since z is equal to square root of x squared plus y squared. In this case, for vector A, it would be the square roots of 4 squared plus 3 squared, which equals 5, since 16 plus 9 is 25, and the square root of 25 is 5. The magnitude is a scalar value. For example, a velocity vector, its magnitude would be speed. Now, you can tell me whether displacement and distance, which is a vector and which is a magnitude. You can take some time to think about it. Displacement and distance, which is a vector and which is the magnitude. Now let's talk about unit vectors. Unit vectors have a magnitude of 1. They're denoted with a caret or a hat, like this. A, the vector A, the unit vector A, is denoted with a caret or a hat. To calculate the unit vector of another vector, we do x hat is equal to the vector x divided by the magnitude or the length of x. You're basically squishing it down by its length, dividing it by its length, so you get the same direction but with a magnitude of 1. So let's do it with let's find out what the unit vector of A is. Since we know that the vector A is 4, 3, and we know from before that the magnitude is 5, the unit vector A would be 4 over 5 and 3 over 5. We distribute this division to each element of the vector. And to verify, the magnitude of A is going to be 4 over 5 squared plus 3 over 5 squared, which is equal to 16 over 25 plus 9 over 25, which is equal to 25 over 25, which is just 1. So we have verified that this is the unit vector A with a magnitude of 1. So what does that look like graphically? We have the vector A, and this would be the unit vector A. It has the same direction, but a magnitude of 1. Now, let's cover some vector operations, specifically vector addition and subtraction. So you can add and subtract vectors, but what does that look like graphically? So if we have vector A and vector B, to add them, we place them end to end, and we connect from the origin to the endpoint. So this is vector A plus vector B equals C. It is the process of combining both the x components and both the y components. You can also visualize this as drawing a parallelogram. For example, we have vector A and vector B as before, but we can also take vector B, place it over here, take vector A, place it over here, and connect it as a parallelogram. Then we connect both ends of the parallelogram from the origin to the end, and as you can see, they are the same vector. Numerically, we add vectors component by component, adding the x components together and then separately adding the y components together. So, as an example, let's say vector A is 4, 3, and vector B is 1, 2. How do we add these together? Well, vector C, which is A plus B, would be 4, 3 plus 1, 2. And we add them separately. So 4 plus 1, 3 plus 2, which would become 5, 5. And that's the vector C. Similarly, with subtraction, vector A minus vector B is 3, 1, because 4 minus 1 is 3, and 3 minus 2 is 1. Pretty simple. Now, let's talk about linear independence. So a set of vectors is linearly dependent if no vector in the set can be written as a linear combination of the other vectors. So what that means is vectors are independent if there's no way to add or scale the other vectors in the set to recreate any particular vector. And this tells us about the relationship between vectors. So here's a mathematical formulation. A set of vectors is linearly independent if the only solution to the equation C1 v vector 1 scalar 2 times vector 2 plus and so on to scalar n vector n equals 0 is C1 equals C2 equals Cn equals 0. So, vectors are linearly independent if the only solution to this equation is if all the scalars are equal to 0. So, if there were any set of scalars that aren't 0 but add up to 0 when you multiply them by the vectors, then they would be linearly dependent. And 0 here is the 0 vector. In machine learning, features or columns of a dataset should be linearly independent to avoid redundancy, which leads to overfitting. In the previous figure, we cannot make C from A, or we cannot make A from C, but we can add A and B to make C, so they are dependent. Here are some more examples of linearly independent vectors. If you have vector 1, vector 2, and vector 3. There's no way to combine these vectors to make the other one. Thus, these are linearly independent vectors. And these vectors are also known as the standard basis vectors for R cubed. R cubed meaning the 3D space of real numbers. Standard basis vectors. And some examples of linearly dependent vectors are if v1 is equal to 2, 4 and v2 is equal to 1, 2. 2 times v2 is equal to v1, which means these are linearly dependent. Here's another example. v1 equals 1, 0, 0. v2 is equal to 0, 1, 0, and v3 is equal to 1, 1, 0. You may be able to figure out that v3 is equal to v1 plus v2. Thus, these are also linearly dependent. Another criteria is if a set of vectors is linearly independent if and only if one of the vectors is in the span of another one. Any such vector may be removed without affecting the span. So what is a span? A span is the set of all linear combinations of the vectors in a space. So, if a vector can be removed and doesn't affect the span, the set of vectors is linearly dependent. So, you can think about this. What is the span of a single vector? What about two vectors? What if the vectors are pointing in the same direction? And what is the span of the zero vector? Just a few questions to think about. Now, let's talk about vector multiplication, specifically dot products. So, what is a dot product? We denote it like this. The vector D is equal to the vector A dot vector B. The dot product generates a scalar value from the product of two vectors. Do not confuse this with the cross product, which would be vector A equals A cross B. These are not the same thing. The dot product is calculated by multiplying the x product, then multiplying the y components, then adding the products together. So, if we had A dot B, which from the previous example is 4, 3, and 1, 2, and we do the dot product of both of these, we do 4 multiplied by 1 plus 3 multiplied by 2. We multiply the x component separately, the y component separately, and we add them together. This equals 11. Thus, A dot B is 11. Further, if we had the vectors 4, 3, 1 dot 5, 6, 7, this would be 20 plus 18 plus 7, which is 45. Here are some rules for the dot product. A dot B is the same thing as B dot A. A dot B plus C is equal to A dot B plus A dot C. This is the distributive rule. C multiplied by A, the scalar C, dot B equals C A dot B and A dot CB. This is basically the associative and commutative properties. Another way to calculate the dot product is A dot B is equal to the magnitude of A times the magnitude of B times cosine theta, where theta is the angle between the two vectors. Now, what's the dot product when theta is 90 degrees? Something to think about. Now let's talk about vector multiplication cross products. So what is the definition of a cross product? A cross B, the cross product of two vectors A and B, is defined as a vector C that is orthogonal or perpendicular, which means a 90-degree angle to both A and B. The magnitude of C is equal to the area of the parallelogram that both vectors span. So here is a 3D graph of what that looks like. This is the x-axis, this is the y-axis, and this is the z-axis. So if we had the vector A and the vector B, and the parallelogram that both of these span is the magnitude of the vector C, which is perpendicular to both A and B. So in this diagram, if it's not clear, A and B are flat along the x and y axis, so they're just two-dimensional, and C is straight along the z-axis. You can visualize this with the right-hand rule, where your index finger is the vector A, your middle finger is the vector B, and your thumb would be A cross B. Here are some properties of the cross product. A cross B is the negative of B cross A. This is called anti-commutativity. A cross B plus C is equal to A cross B plus A cross C. So the distributive rule applies here as well. A constant or a scalar multiplied by A cross B is equal to C times A cross B, like that, or A cross C times B. Sorry, not a vector, just a scalar. The magnitude of A cross B is equal to A, the magnitude of A, times the magnitude of B, sine theta. Contrast this with the magnitude of the dot product. The value of the dot product, which is magnitude of A times the magnitude of B times the cosine theta. So the magnitude of A cross B is magnitude of A, magnitude of B times sine theta, where theta is again the angle between A and B. So here's the mathematical formula for the cross product. If we have the vector A, which is equal to A1, A2, A3, the values, and B is B1, B2, B3, and C is A cross B. How do we find the cross product? By arranging these vectors. What we do is, the vector C is I, J, K, A1, A2, A3, B1, B2, B3. This is how we arrange them, where I is equal to 1, 0, 0, J is equal to 0, 1, 0, and K is equal to 0, 0, 1. These are basis vectors. And how we calculate them is A2 times B3 minus A3 times B2 multiplied by I, A1 times B3 minus A3B1 times J. Here's a minus. Keep note of that. Plus A1 B2 minus A2 B1 of K. So we take we take I, and it would be A2 times B3 minus A3 B2, and we multiply it with I. Then we subtract J, which is A1 times B3, and A3 times B1, and multiply that. And then we add K with A1 B2 and A2 B1. That's how we calculate the cross product. Here's an example. A cross B is equal to IJK, and let's say A is 3, negative 3, 1, and B is 4, 9, 2. If you solve this out, you'll get negative 15I minus 2J plus 39K equals negative 15, negative 2, and 39. Go ahead and calculate this out based on this formula here, and you'll see how we got to this result. Go ahead and do that for practice. Now, let's talk about vector spaces. So vector spaces are just the space in which vectors live. And the definition is of a basis set is a linearly independent set of vectors that when used in linear combination can represent every vector in a given vector space. So that's the definition of a basis set. Again, a basis set is a linearly independent set of vectors when used in linear combination can represent every vector in a given vector space. Now let's talk about matrices. Like a vector, a matrix, and the plural of matrix, matrices, like a vector, a matrix is a collection of numbers, but it's a table of numbers rather than a list. Vectors are matrices with one column or one row, and many vector operations apply equally to matrices. For example, matrix addition. How do we do matrix addition? We add and subtract element by element. So A plus B equals C. If we have the matrix A11, A12, A21, A22, and the reason why we denote them this way is here is A in the first row, first column, first row, second column, second row, first column, and second row, second column. And we add it with B11, B12, B21, B22. The result would just be A11 plus B11, A12 plus B12, A21 plus B21, and A22 plus B22. We just add them element wise. Now, the same thing works for subtraction as well. We would just switch this with a subtraction sign. Same here. Now, let's move on to matrix multiplication, which is a bit more complicated. here we say AB is equal to D. If we have the vectors A and B, and we multiply them together, how does this work? Well, what happens is we take A11 times B11 plus A12 times B21. Here is A11 B12 plus A12 B22 A21 times B11, and I'll explain how this kind of works spatially as well, but for now here's just the formula for it. A22 plus B21 A21 B12 plus A22 B22. So essentially what we're doing here is we're taking the first row and multiplying it by the first column to get this result here. We multiply A11 with B11, A12 with B21, and that's how we get this. How we get this is the first row multiplied with the second column. This is the second row and the first column, and this is the second row and the second column. They do not need to be the same size to multiply. Two matrices can be different sizes and multiplied, but the number of columns in the first matrix must be equal to the number of rows in the second matrix. So, the matrices need to be of this shape. The number of columns in the first matrix and the number of rows in the second matrix need to match. And the product of this m times n matrix and n by k matrix, meaning n rows, k columns, m rows, n columns, is a m by k matrix. It's just this by this. Now, let's talk about determinants. Think of each column of a matrix to be a vector. Some matrices stretch space out and others squeeze it in. You can think of a matrix as transforming space. The scaling factor of which matrices stretch space out or squeeze space in is called the determinant. So if we had the matrix 1, 0, 0, 1 as columns, we think of each column of a matrix to be a vector, as I said. So this would be the first vector, this would be the second vector, and the area, if you think of the area of this, the area would be 1.0, since 1 squared is just 1. But if we had another matrix with the columns 2, 0 and 1, 2, how do we draw this out? Well, we would have the first vector be 2, 0 and the second vector be 1, 2. And then the way to represent the area of this one would be as a parallelogram here. And the area of this would be 4. It would just be base times height. So you can see how different matrices stretch out space differently. We have this vector, this matrix, which represents an area of 1, and this matrix, which represents an area of 4, stretching the area out. Now let's figure out how to actually calculate the determinants of a matrix. How much does a matrix stretch or squeeze space? So if we had the determinant of this matrix here, 1, 2, 3, 4, 5, 6, 7, 8, 9, how do we find the determinant of this? Well, it's similar to how we find the cross product in a way. I'll describe it spatially later, but formulaically first. We take the determinant of 5, 8, 6, 9. We subtract it with 4 times the determinant of 2, 3, 8, 9. And we add it with 7, 2, 3, 5, 6. Sorry, the determinant of this. So essentially what we're doing is we're taking 1, multiplying it by the determinant of this, 4 multiplied with the determinant of this, and 7 multiplied by the determinant of this. So how do we find the determinant of a 2 by 2 matrix? Well, we take the elements, we multiply them together this way, and then subtract it with the product this way. And we do that for each of them. So it would be 2 times 9 minus 3 times 8 plus 7 times 7 times 2 times 6 minus 3 times 5. This equals 1 times negative 3 minus 4 times negative 6 plus 7 times negative 3. And this actually equals 0. Since negative 3 minus negative 24 plus negative 21 equals 0. Hopefully you can see the connection here to the cross product, how it's derived and calculated spatially. Next, let's talk about linear transformations. Linear transformations are a special subset of functions that take vectors as inputs. So we say that the vector y is equal to the matrix x times the vector x. All matrices are linear transformations, but not all linear transformations are matrices. Consider A is equal to 0, negative 1, 1, 0. When multiplied with 4, 3, we get negative 3, 4. Let's graph this out. If we graph 4, 3, we get this vector, and negative 3, 4. We get this. This is a 90-degree angle. What about 1 A times 100, 0. It transforms to 0, 100, which is a 90-degree rotation counterclockwise, just like this rotation. A is a rotation matrix. This is not a coincidence. The general rotation matrix to rotate a vector by angle theta. To rotate a vector by angle theta, the rotation matrix is equal to cosine theta, sine theta, negative sine theta. Sorry, not like this. Times cosine theta. A few other useful linear transformations, or operators, include the identity transformation, stretch and squash, skew, and flip. Linear transformations can also be known as operators, and operators can actually be multiplied together. Now let's talk about eigenvalues and eigenvectors. Let's say we have a square n by n matrix A. Eigenvectors have a special relationship with matrix A, so that when you multiply A times the eigenvector x, you get back that same vector multiplied by a scalar lambda. So you have eigenvector x and a scalar lambda, which is drawn like this. So we say that A, the matrix A, the square matrix n by n matrix A, times the vector x is equal to the scalar lambda multiplied with the vector x. The scalar lambda is also known as an eigenvalue, or a characteristic value. Eigenvectors must be non-trivial, which means they cannot be the zero vector. A matrix can have multiple eigenvalues, but no more than its number of rows and columns, and each eigenvalue is associated with a specific eigenvector. So, when we find the eigenvalues, then we can solve for the eigenvectors for each of the eigenvalues. So, in action, let's say that A, the square matrix A, is equal to -3, -2, 1, 0. And x equals 1, 1. We want to verify that ax is equal to lambda x. Ax is actually equal to -2, -2 when we multiply them together. Again, we take the first row and this column, and the second row and this column, and we get -2, -2, which is equal to -2 times the vector 1, 1. Here is the eigenvalue, and this is the eigenvector. The eigenvector x that we have found above, that we have specified above. Now, how do we solve for eigenvalues and eigenvectors? Let's move this up. So let's derive how we solve for eigenvectors and eigenvalues. Given the square matrix X, we know this, that the square matrix times the vector X is equal to the scalar, the eigenvalue, times the eigenvector X. If we manipulate this, we can see that this is true if we subtract lambda x on both sides. Now, if we insert the identity matrix, which is basically like multiplying by 1, where the identity matrix is any size matrix with 1 in its diagonals and zeros everywhere else, and it could continue onwards, or it could be a matrix of size 2 like this. It's basically any size matrix with 1s along its diagonals and zeros everywhere else. And inserting the identity matrix or multiplying it is basically like multiplying by 1. So this, like this would be the same as what is above. Now let's factor out the x. What we need to know here is that this cannot be 0. The reason why it can't be 0 is if it was 0, then the eigenvector could be any value and this would be true. But we need to know that there are specific eigenvalues to solve for this equation. For the same reason, the eigenvector x cannot be 0 either, as we have specified before. The eigenvectors must be non-trivial, which means they cannot be the 0 vector. Now, if this matrix were invertible, meaning the inverse of this matrix, denoted -1, multiplied on both sides, basically what the inverse matrix does is it cancels out the multiplication of the matrix. So this would become x equals 0. If this matrix were invertible, it would mean that the eigenvector x could be equal to 0. Therefore, this matrix can't be invertible because we know that the eigenvector cannot be must be non-trivial, which means it cannot be the 0 vector. Therefore, this matrix can't be invertible, which means the determinant has to be 0. When a matrix is not invertible, it means the determinant has to be 0. So, the determinant of a minus lambda I is 0. This is called the characteristic equation, and the solution to this equation will be eigenvalues. So we solve this equation and we get the eigenvalues that we are looking for. Here's a concrete example. If A is equal to the matrix 1, 4, 1, 1, then A minus lambda I would be equal to 1, 4, 1, 1 minus a lambda, and the identity matrix of the same size as A, which is equal to 1, 1, 4, 1 minus lambda, 0, 0, since we multiplied the lambda with the identity matrix. And this, since we just do element-wise subtraction, will be 1 minus lambda, 1, 4, and again 1 minus lambda. We know that the determinant of this matrix has to be 0. That's what we found before. That's the characteristic equation. And how do we find the determinant? Again, we do this multiplied together minus this multiplied together. So let's go ahead and do that. 1 minus lambda multiplied by 1 minus lambda minus 4 times 1 equals 0. If we expand this out, what we get is 1 minus 2 times lambda plus lambda squared minus 4 equals 0. Hopefully you know and understand how we got to this. We just expand this out. So, to simplify this further, we get lambda squared minus 2 lambda minus 3 equals 0. And we can factor this out using some algebra. Lambda minus 3 multiplied by lambda plus 1 is equal to 0. And if you remember from algebra, how do we find what the eigenvalues are? We just figure out what does the eigenvalue have to be for this to equal 0, and what does it have to be for this to equal 0, so that when multiplying it, it would equal 0. So the eigenvalues must be 3 and negative 1. Now that we have the eigenvalues, we solve for the eigenvectors, and it must be done for each eigenvalue separately. So again, a minus lambda I multiplied by the x vector, the eigenvector, is equal to 0. So we will plug in an eigenvalue to get a new matrix. Then we'll end up with a system of equations to solve. To solve, we use elementary row operations to get it into row echelon form. And I'll discuss what row echelon form is in a bit. We will sometimes have to choose values for the components of the eigenvectors. The solution of this equation gives us only the form of the eigenvector. Any scalar multiple of the answer is also an eigenvector. So let's write this out so it's a bit more understandable. So the multiple is also an eigenvector by definition. So again, A is 4, 1, 4, 1, 1. We know that the eigenvalues are 3 and negative 1. And we know that A minus lambda I multiplied by the eigenvector equals 0. So if we plug in the eigenvalues into this characteristic equation, this equation here, we get a minus 3i equals 0, which equals 1, 4, 1, 1 minus 3, 0, 0, 3, which is just the eigenvalue 3 multiplied by the identity matrix I. And what we get is negative 2, 1, 4, negative 2. Now to get this into row echelon form, what we do is a simple elementary row operation. We take the second row and add 2 times the first row to it. So we take the second row and we add 2 times the first row to it. So what happens is we get negative 4 here and 2 here, and we add them together, and what happens is we get zeros on the bottom because the negative 4 and the 4 cancel out, and then 2 and the negative 2 cancel out. And we're left with this matrix, which is in row echelon form. And just to quickly understand what row echelon form is, there's 2 rules. All rows of zeros must be at the bottom, and there must be a staircase pattern of the first non-zero entries in each row. So this is a valid row echelon form matrix because all the rows of 0, fully 0, are at the bottom, and there's a staircase pattern. Now I'll show you an example of what an invalid row echelon form would be. If we had 1, 2, 3, 4, 0, 0, 0, 0, 0, 0, 0, 2, 1, 1, 2, and 0. So we have no rows of full zeros, so that's fine. But the staircase pattern looks like this. And this is invalid because the staircase pattern necessitates that we don't go down 2 rows at once. So this is not a valid row echelon form. Now let's continue where we left off. We left off with this matrix negative 2, 1, 0, 0, which we got from here. And we know that a minus 3i multiplied by x, the eigenvector x, is equal to the 0 vector, which means that since we know a is negative 2, 1, 0, 0, and this is x1, x2 equals the 0 vector, a minus 3i is equal to this, and here's the x vector here. What we get is, when we multiply these out, we get 2x1 plus x2 equals 0, x2 equals 2x1, and if we choose, let's choose x1 equals 1, then we get x2 is equal to 2, and thus the vector x, the eigenvector x, is equal to 1, 2. Now let's say we chose 2 here instead, then we would get 2, 4, or 3, 6. So what this means is that any multiple of this vector also works. So the eigenvector can be c and 2c, where c is any constant value. So can you solve for the eigenvector for the eigenvalue negative 1? I've already solved it for the eigenvalue negative 3, for positive 3. So go ahead and solve it for the eigenvalue negative 1. The solution of that, it would be 1, negative 2, or c, negative 2c. Go ahead and solve it and see how we got to that answer. For more practice, solve for eigenvalues and eigenvectors of these matrices. And for the eigenvectors, 1, 1, negative 5 over 3, and 0, negative 2, 1. Go ahead and solve this for more practice as well. So geometrically, what is an eigenvector? Let's try and understand this. An eigenvector x of a matrix A is a vector that does not change direction when multiplied by A. So, as I said before, a matrix can be thought of as a linear transformation. So when you multiply A by the eigenvector x, when you apply the linear transformation to that vector, the eigenvalue is a value. The eigenvector does not change direction when you multiply by the linear transformation. It may scale, it may squeeze, but it doesn't change direction. An eigenvalue is the value of which the vector scales or squeezes when multiplied by A. Now let's talk about solving systems of linear equations with matrices. So let's solve. X plus y plus z is equal to 6. 2y plus 5z is equal to negative 4. And 2x plus 5y minus z is equal to 27. We can view these as matrices, where we take the constants of x, y, and z. So 1, 1, 1, because of the invisible constant 1 here. We do the same for the other equations. Multiplied by the vector x, y, z. And it should equal what each of the equations equal. 6, negative 4, 27. This is A multiplied by X equals B. So you can multiply these two matrices together and notice how they're formatted to represent the system of equations. You can go ahead and do that for practice. Multiply the matrices together and see how they represent this system of equations. The solution to Ax equals B is X equals the inverse of A times B. The inverse of the matrix A, in this case, is 1 over negative 21 times the matrix negative 27, 6, 3, 10, negative 3, negative 5, negative 4, negative 3, and 2. Now, sometimes matrices do not have an inverse, but in this case it does. We'll see how to calculate the inverse soon. But to verify what is x, which we know is the inverse times b, let's go ahead and solve for that. X, y, z is equal to 1, negative 21 times the vector A this equals, when you multiply it with b, five, 3, negative 2. So these are the values of x, y, and z. So how do we find the inverse of a matrix? We use something called the Gauss-Jordan method. Basically, we turn it into an augmented matrix where AI is equal to, through elementary row operations, it becomes I inverse negative 1. So whatever operations we apply to A, we apply to the identity matrix, so that A becomes the identity matrix, and then the identity matrix will become the inverse of A. I'll show an example of this in a bit. But elementary row operations can be adding rows, multiplying rows, or swapping rows. So let's find the inverse of A. Where A is the matrix here. So we start with the augmented matrix. Now, let's apply some elementary row operations to ideally turn A into the identity matrix. The first row operation that we're going to apply, and this is kind of an art, reducing the matrix A into the identity matrix. It's kind of fun. It's like solving a puzzle. The first thing that we're going to do is R2 plus R1, and we're going to apply that to R1. So what will happen is R2, we're going to add that to R1. So R1 will become 5, 0, 0. Row 2 and row 3 will stay the same. And keep in mind, we have to do the same transformation, the same elementary row operation to the identity matrix. So it will become 1, 1, 0, 0, 1, 0, 0, 0, 1. Now from here, what can we do? As you can see, we've turned this 2 into a 0, which makes it closer to the identity matrix where there are 2 zeros here. So we want to step by step reduce the matrix A into the identity matrix. So next let's do row 1, and let's divide it by 5 to turn this 5 into a negative 1. A positive 1. So we can do row 1 divided by 5 and apply that to row 1. We'll get 1, 0, 0, 2, 0, negative 2, 0, 1, 1. And we do the same row operation to the matrix that we have on the right side. And we get 1/5, 1/5, 0, 0, 1, 0, 0, 0, 1. Actually, let's use decimals here. 0.2 and 0.2. Next, we're going to do row 2 minus 2R1 and apply that to row 2. And it becomes 1, 0, 0 on the top row. It stays the same. 0, 0, negative 2, 0, 1, 1. The third row stays the same. And we do the same thing to the matrix on the side. 0.2, 0.2, 0, negative 0.4, 0.6, 0, 0, 0, 1. As you can see here, we've turned this into a 0 as well, making it closer to the identity matrix. The next thing we're going to do is negative 1/2 times R2 and apply that to R2. What happens is 1, 0, 0, 0, 0, 1. This negative 2 from here turns into a 1 here. And 0, 1, 1. Then we do the same thing on the right side. So this negative 0.4 and 0.6 have been turned into 0.2 and negative 0.3. The next thing we're going to do is swap R2 and R3. So now it looks almost exactly like the identity matrix, except for this one over here. Do the same thing on the right side. Now one final operation. R2 minus R3, and apply that to R2. We get the identity matrix, and we do the same thing on the right side. And this is the inverse matrix of A, and that's all. We found the inverse. Now, here's another example of solving a system. On the left, we're going to have the system of equations. In the middle, we're going to have the row operations. And on the right, we're going to have the augmented matrix. So here's a similar method, but organized a little bit differently. So let's say the system of equations we have is 2x plus y minus z is equal to 8 minus 3x minus y plus 2z is equal to negative 11. Negative 2x plus y plus 2z is equal to negative 3. And let's set up the matrix on this side. We take the coefficients 2, 1, negative 1, and we put what it equals to on the side. And now we apply row operations so that we turn this matrix here into the identity matrix, and what's left here when we apply the same operations, this will be x, y, and z. So let's start off with so now that you understand how this method works, finding an inverse, Okay, let's start with these row operations. L2 plus 3 over 2 of L1 applied to L2, and L3 plus L1 applied to L3. So since only row 2 and row 3 are changing, we'll keep row 1 the same. This becomes 1/2 y plus 1/2 z equals 1, and 2y plus c equals 5. Hopefully you can see how we got there. Then we do the same thing on this side. 2, 1, negative 1. The row 1 stays the same. 0, 1/2, 1/2, 0, 2, and 1. And this becomes 8, 1, and 5. Next, let's do L3 plus 4L2 and apply that to L2. Sorry, let's apply that to L3. 2x plus y minus z is equal to 8. 1/2 y plus 1/2 z is equal to 1. They both stay the same. And negative z is equal to 1. We're only changing row 3. Now we have 2, 1, negative 1, 0, 1/2, 1/2, and 0, 2, 1. And on this side, we have 8, 1, and 1. Now this matrix is in row echelon form with the staircase pattern and these zeros below the staircase. Now let's do L1 minus L3 applied to L1, L2 plus 1/2 of L3, and applied to L2. The equations become 2x plus y equals 7, 1/2 y equals 3 over 2, and a negative z equals 1. The matrix then becomes 2, 1, 0, 0, 1/2, 0, and 0, 0, negative 1. And this side becomes 7, 3 over 2, and 1. Next, let's do 2 times row 2 applied to row 2. And let's negate the third row. That makes 2x plus y remain as 7, y equal to 3, and z equal to negative 1. Which turns the matrix into 2, 1, 0, 0, 1, 0, 0, 0, 1. And on this side, 7, 3, negative 1. Now finally, L1 minus L2, let's apply that to row 1. 1/2 of row 1, apply that to row 1. We're kind of combining two operations here. And that makes x equals 2, y equals 3, and z equals negative 1. And to demonstrate with the matrix, we get 1, 0, 0. We get the identity matrix. And that's all for linear algebra. I've separated and split probability and statistics and calculus into the next videos in the machine learning mastery playlist, so you can go ahead and check them out there. Thanks for watching, and I hope to see you in the next one.